All right, so we're going to start with this is chapter 8 in your text, periodic relationships among the elements. So briefly, not much about its history, just sort of a background, and and then we'll get into why it's organized the way it is, why it's useful, and certain trends that become apparent uh, once you become familiar with it. So over time, we it's one of the great achievements of chemistry is that we have essentially discovered all of the elements in the universe. And that's true. There's some not represented on the table that have been some supercomputers have basically predicted there's a cluster of elements that are highly unstable, almost all radioactive, and or I guess they all are radioactive and totally not useful. But we have discovered all of the elements in the universe. And you can see that before there was a periodic table in ancient times, only a few different elements were found. These are the ones that were very abundant on Earth. They still are, and extremely useful to early man. You can see copper, silver, gold, lead, or mercury, iron, tin, that's lead, carbon, of course. Basically, anything left over after a fire is more or less pure carbon, and then sulfur. In the medieval ages, they started filling in, finding some more elements, but it really wasn't until the scientific revolution that we really started filling up this table. And it was Mendeleev who took all these different elements that were being documented and discovered and what properties they could determine about each element. He compiled and basically made a periodic table that resembles the one we see today. Of course, without some of the elements, but for the missing elements in his periodic table, he was able to predict the properties such as melting point. Not sure he could predict the valency of certain groups, but basically the molar mass and other straightforward properties of the elements. And the lanthanides, actinides, in your book, they refer to them as the lanthanoids and actinoids. So I guess that's interchangeable. They must have switched that in the last 10 years or so. But anyway, you're not responsible to memorize this. It's just interesting to look at. So the way the periodic table is organized is what we have are 18 vertical columns. I don't know if you can see this, my cursor right here. I suppose I can hit control every once in a while to bring your attention to it. But you have 18 vertical columns, and these are the groups. So 1, 2, 3, and so on. The periods have to do with these rows right here. So you have the first period, it's just hydrogen and helium. Second, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. In chemistry, we're primarily interested, at least you guys are, with the organic chemistry, meaning living things, was with these guys right here. And organic chemistry has to do with chemistry compounds that contain carbon, at least one carbon to something else bond. But anyway, so representative elements, it's in dark blue. These are the alkali metals and alkaline metals over here. I'm going to make my cursor bigger. Transition metals, group 12, and then 13, 14, 15, 16, 17. This is where a lot of our chemistry is going to happen. And we're primarily interested in this period right here. Although, it's good to be aware. These become the elements below in higher periods, but lower on the periodic table, are more exotic, and their chemistry is well understood, but as far as undergraduates are concerned. You don't have to know as much about them. So the lanthanoids, as I mentioned, and the actinoids are down here. So the way this is represented is this gap right here is we would put this section right there, and then the periodicity of the table continues here. But this is sort of a chunk that was taken out, and they have their own sort of set of reactivities and such. We'll go into the different groups and their different properties, but the transition metals are very interesting, extremely useful. For instance, their oxidation states can vary a good deal. Most of them have variable oxidation states, and that makes them good for catalysis. Anyway, before we go on much further about the trends, you guys are going to be responsible for understanding the electron configuration of different elements. And it's not too difficult if you have a couple of things. If you keep a few things in mind, I'm not sure where to put my mouse. But so we can see here, basically from a previous chapter, we talked about the electronic nature of the atom. And there are different shells and subshells where electrons reside. They reside in these orbitals. And you can see here we have hydrogen 1s1, helium 1s2, and then we go down 2s1, 2s2, and then for boron 2s2, 2p1, and so on. And it looks a little overwhelming, and it certainly can be tedious to keep track, but you need to be able to, you're always going to have a periodic table that you can look at and use to figure out, various things such as the electron configuration. And so there's actually two ways you can go about figuring out the electron configuration of any of these elements. There are some exceptions to this, but you're not going to be responsible. Most of those exceptions are in the transition metal range. So next slide, the Aufbau principle. So in the ground state of an atom or ion, electrons fill subshells of lowest available energy first, then higher energy. In nature, everything wants to be as low energy as possible. So you can see here the orbital shell blocks. For our purposes, there are only 4. It does go to G and beyond. So S, P, D, F, G, and I think that's about it. But that's with the more exotic elements. So you can see here, this looks weird, right here, right? But on a test or a quiz, what you can do, so Aufbau. Principle. My tablet seems to be glitching a little bit. Let's hope it doesn't mess up too much. Just building up. Build up. Microphone's kind of in the way. Build up electrons. And this is, of course, a sort of abbreviated definition. Lowest energy first. And so the recipe for this, if you were, say, on a test and you did not have a periodic table, which would be unusual, going by the slide to the left, you can make a couple of columns and you just go down sequentially. So 3s, we can keep going, 6s. But starting, you make this first column, and then the p orbitals, you start with in the second row, 2p, 3p, 4p, 5p, 6p, and then so on. So 3d and you're saying that these actually don't represent, they're not in order of how these different electron configurations are. Like if we go down here, you'll notice that it starts at 4s2, and I'll explain that in a moment. 4s2, well, we keep going down and it's like 5s2. Well, if you look more closely at this slide, you can see it goes starting from, I guess, up above and to the right. It goes down to the left this way. And I'll draw this in a more suggestive way in just a second when I finish doing these. So going down one more, we don't have to do a complete one, 5F, 6F. So from here, I guess I can do it in a different color. I could have made this bigger so it's easier to see. So then we have 2S, 2P, 3S, 3P, 4S, and then this is kind of a longer one, 3D, 4P, 5S. That's not a very straight line. I can do better. And then 4D, 5P, 6S, and so on, right? And so from this, I don't know why it's glitching like that, you can write out the electron configuration of anything. So what it would be is, well, we'll just assume each one is filled as I go up. So 1s2, right? Let's change colors. 1s2 up here, 2s2 here, 2p, and I forgot to mention, yes, 6. So in S's, there are two electrons. P's can hold 6 electrons. D's can hold how many? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. And then the F's, I think it's 16, my goodness. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But those are fairly exotic. The reason why I haven't memorized that is because I haven't done any chemistry with the lanthanoids or actinoids. But 15. So from this, getting back to here, we can build up the electron configuration of any element. So right here, if you can see my cursor, we do 1s2, 2s2, here, 2p6, and then now we're at 3s2, and then what comes next? So 3p6, 4s2, 3d10, 4p6. So looking at this, having no background in chemistry and not having read the chapter or seen a lecture about it, this looks incredibly intimidating. Well, you have two ways to go about figuring out what the electron configuration is for any of the atoms. You can use the Aufbau principle, and then this little study, I forget what it's called. It's like a, anyway, it's a graphical, it's the different orbitals organized in such a way that you can quickly figure out the correct order for the electron configuration of anything. Or if you have, I wish I could draw on this slide, I'll figure that out later. I guess I could save it as a PDF. I had trouble making it just a single one. You can just know that 1s1, 1s2, if you can remember this picture right here, you can build it up that way. So there are two different ways that you can go about it. I'm going to change back to white. So It'd be nice if I had the periodic table at the same time, and I suppose I could do that. Let me pause right now. All right, getting back to it. Just realized I've already been talking for 15 minutes, so I'll finish up, find a good spot to take a break, and then continue with some of the other material. So, Aufbau principle, 2 different ways to figure out the electron configuration of a different element. So, from a prior chapter, you guys know that atoms, essentially, the exterior is made up of electrons. Well, the properties of the different elements have to do a lot with their electron configuration, but especially if there's a positive or negative charge on it. So as here we're talking about isoelectronic species, which more or less just means that 2 different elements can have the same electron configuration, and that can happen several different ways. One can gain an electron, another one can lose an electron. And so in the example we have here, sodium. Actually, let me bring my periodic table here, and I might want to do. All right, here's a periodic table. I think the bottom is cut off a little bit. All right, that's better. So here we have sodium, right? If the electron configuration starts out, so 1s2 and so on, 2s2, 3s2, or this would be 3s1. If we lose that 3s1, it has the electron configuration of neon, which is a noble gas and very stable. Maybe I haven't gone into that at all, or certainly not enough for you guys to appreciate that. But the summary is that the noble gases are called such because they are unreactive. They have a full electron shell, external shell. So because it's full, they're happy as is, and they don't want to lose one, they don't want to gain one, and essentially you can think of all the other elements are striving to become more like the noble gases. So in the case of sodium, which is over here, if it loses one, that's the quickest way that it can resemble neon in regards to the electron configuration. Now it still has the same number of protons, so it has a positive charge on it. So that's what this is getting at right here. Sodium resembles neon when it has a positive charge. Aluminum, which we have right here, let's see, if it added 1, 2, 3, 4, 5 electrons, it would be similar to argon. It's not going to do that. That's way too many electrons, and there's many good reasons for that. But if it loses 1 electron, it would be like magnesium, which is very reactive. Loses a second, be like sodium. But if it loses a third, it also is going to resemble neon, and at least have the identical electron configuration. So fluoride, similar or just like the other halogens, if you add an electron, it's going to be like neon here in the case of fluoride. And the same thing for chloride, or similar to chloride. If we add an electron to chloride, it's going to be like argon. And if we add one to bromine, it becomes bromide, and it's like krypton. So a lot of these typical charges that you see on different elements is because when it has that charge, it has the electron configuration of a noble gas. So these are all isoelectronic with neon. Chloride anion is isoelectronic with argon. Bromide, negative, isoelectronic with krypton. And then these guys over here, they prefer to lose electrons. So like lithium plus, 1 plus, is isoelectronic with helium. Beryllium 2 plus, 1 electron loss. It's like lithium, second one, and it has the same electron configuration as helium. And same thing here. Magnesium 2 plus is isoelectronic with neon. And Na1 plus we've already covered. All right. So it gets a little bit more complicated with transition metals. Without going too deeply into it, well, let's see what they say here. When a cation is formed from an atom of a transition metal, electrons are always removed first from the ns orbital and then from the n-1d orbitals. If you go back to Aufbau, you can see, so S is up here, and then it goes from the P, when we're all the way down here at 5S, the 3D, or I'm sorry, yeah, 5S, 4P, 3D. Oh, let's go back here. So 4S, 2, 3D, 6. If it loses 2, and iron doesn't just typically lose 1, it loses 2 or 3. It's going to lose it from the S orbitals here. And then that's the same as the 3D6. So hopefully you've read this chapter, and I guess I'd skipped over this. The noble gas configuration, electron configuration that you're seeing here, this is just sort of a shorthand. As opposed to write out the electron configuration each and every time, what we allow is that you can put as sort of the base the electron, the noble gas associated with the electron configuration. So for iron, for example, since we're there right now, argon, it has this electron configuration, so 1s2, 2s2, 2p6, 3s2, wait, I totally forgot which, oh, okay, so on and so on. And so instead of writing all those out, we'll just put argon and then start here at the 1, 2, 3, 4s2, and then what is that? That's the 3d 5 is what we're talking about right now, or 4s0 3d5 for iron 3, and then 3d6 for iron 2. Anyway, so moving on, I'm going to take a break in a second so that you guys, I don't make any videos that are too long. We're already 23 minutes right now. The next thing we're going to talk about, and maybe I'll do some background too and some fundamentals that I think I missed in the beginning, but periodic trends are very important for understanding reactivity. And so some of these trends, some of the trends, and there really aren't too many, is ionization energy, atomic radius, electronegativity, electron affinity, and metallic character, which is less important. But all these, the trends are fairly easy to memorize, and they're incredibly useful when you're at least looking at reactivity. So I'll stop there, and I'll make another video that begins here.